Would you accept an answer that is at most twice as costly as perfect if perfect might take 1,000,000 years? Approximation algorithms make that bargain honest by proving how far from best they can be. Anchor example: a delivery route that is provably within a factor of 2 before trucks leave can beat an exact route that arrives after dispatch. Approximation begins with maturity. Sometimes the honest answer is not perfect, but bounded. By the end, you should be able to read the receipt. OPT is the invisible perfect answer, ALG is what we ship, and the ratio limits how wrong we are allowed to be. To reduce overload, keep only one main promise in focus first. OPT is best possible, ALG is our shipped answer, and the ratio is the guardrail. The useful tension is deadline versus perfection. If the exact solver returns after the decision is already stale, the perfect answer has no practical value. A bounded near answer can be the honest compromise. Approximation is not hand-wavy good enough. A ratio states how far the algorithm's answer can be from the true optimum. For minimization, the algorithm may cost more than optimum, but the proof bounds how much more. The ratio is what separates engineering judgment from wishful thinking. The optimum may be too expensive to find, but it can still be used in the proof as an invisible benchmark. The optimum can be too expensive to find, but the proof can still compare against it. Approximation becomes useful when exact search is too expensive but a random answer is too risky. The algorithm is allowed to be imperfect only because it carries a mathematical limit on how bad that imperfection can be. For minimization, a 2 approximation means the algorithm's cost is at most twice the optimal cost. For maximization, the direction changes. The guarantee says the value is at least some fraction of the optimal value. Pause on the delivery deadline. Would you rather ship a bounded route now or compute the perfect route too late? Keep one scoreboard in your head, OPT, ALG, and the limit line. If ALG crosses the limit, the algorithm loses the right to call itself an approximation with that factor. The promise is not perfection, the promise is knowing how far from perfection you can drift. To prove a guarantee, minimization often compares against a lower bound on optimum, while maximization often needs an upper benchmark or a fraction of optimum. The proof must face the right direction. The proof direction matters because minimization and maximization fail in opposite ways. The guarantee is not measured against a wish. It is measured against the best possible solution for that exact input. That makes the bound meaningful even when we never compute the perfect answer directly. In vertex cover, we choose vertices so every edge is touched. The exact minimum is hard, but a simple matching-based method gives a clean 2 approximation. Pick an uncovered edge, take both endpoints, then remove every edge those endpoints cover. The chosen proof edges stay disjoint, so any optimal cover needs at least one endpoint per chosen edge, while we take 2. Do not let OPT float as a mystery symbol. OPT is the best possible answer, even if we cannot afford to find it. ALG is the answer our algorithm actually returns. The ratio is the scoreboard comparing those two. Set cover asks for fewest sets that cover all elements. Greedy repeatedly chooses the set covering the most remaining elements. Greedy set cover repeatedly buys the set that covers the most still uncovered elements per cost. Greedy set cover is not perfect, but it has a logarithmic style guarantee. The exact bound is technical, the mental model is shrinking uncovered work efficiently. The proof direction matters because minimization and maximization fail in opposite ways. Before reading the inequality, ask whether this is a minimization problem or a maximization problem. The promise is not perfection, the promise is knowing how far from perfection you can drift. Metric TSP assumes distances obey the triangle inequality. That structure allows approximation strategies that would fail for arbitrary costs. If going directly is never worse than detouring, shortcuts become safe. That one assumption powers several approximation ideas. For minimization, bigger is worse, so the guarantee says our cost is not too much above OPT. For maximization, smaller is worse, so the guarantee says our value is not too far below OPT. For metric TSP, a minimum spanning tree can act as a cheap scaffold. It connects everything with low cost, then we transform it into a tour-like route. One friendly intuition is to double the tree edges so every vertex can be walked through evenly, then shortcut repeated visits. Triangle inequality keeps those shortcuts from increasing cost. The proof direction matters because minimization and maximization fail in opposite ways. Some approximation algorithms solve a relaxed version first, then round the answer back into legal discrete choices while controlling damage. Rounding starts with a relaxed fractional answer and turns it into a legal discrete answer while tracking loss. Before the band locks, check which side of the inequality protects the algorithm's promise. The promise is not perfection, the promise is knowing how far from perfection you can drift. Random choices can also support approximation, especially when expected quality can be bounded mathematically. For vertex cover, matched edges are like independent alarms. No single chosen vertex can cover two of those matched edges at once. So the perfect answer must pay at least one endpoint per alarm, while our simple algorithm pays both endpoints. Some problems allow schemes that get arbitrarily close to optimal for a cost in running time. The closer you demand, the more you pay. A PTAS is polynomial for fixed epsilon, but the hidden cost can explode as you demand near perfect accuracy. Some problems are not only hard to solve exactly, they are hard to approximate beyond certain limits. The proof direction matters because minimization and maximization fail in opposite ways. A heuristic without a bound may work well in practice, but it is not the same thing as an approximation algorithm with a proof. The common mistake is calling a good-looking heuristic an approximation without a receipt. A ratio must compare to the true optimum or a valid bound on it. Comparing only to another heuristic does not prove approximation quality. Vertex cover checkpoint: if every matched edge needs one endpoint, why does taking both endpoints stay within factor 2? The promise is not perfection, the promise is knowing how far from perfection you can drift. Approximation is a bargain, less exactness for more scalability, but only when the mathematical receipt matches the risk. For delivery routes it may be perfect, for a safety-critical dose it may not be enough. Use approximation when exactness is expensive, near best is useful, and you can state a guarantee that matches the risk of the application. The proof direction matters because minimization and maximization fail in opposite ways. Set cover shows the other side of approximation: the greedy choice may not be perfect, but it reduces uncovered elements quickly. The analysis charges progress in a way that turns repeated local improvement into a global bound. Approximation is not automatically acceptable. If a medical dosage, legal deadline, or safety-critical control needs exactness, the guarantee must match the real-world risk. This is also ethical design: being close is useful only when the real world can tolerate the gap. Ask, what is the optimum benchmark? Is this minimization or maximization? Which lower or upper bound faces the right direction, and what ratio is acceptable? For vertex cover, choose an uncovered edge, take both endpoints, remove covered edges, and repeat. The selected edges form the proof skeleton. Risk checkpoint: is a bounded near answer acceptable here, or does the domain demand exactness? Metric TSP works because triangle inequality gives permission to shortcut. If going directly is never worse than detouring, a double tree walk can be compressed into a tour without making the route longer. The promise is not perfection, the promise is knowing how far from perfection you can drift. Write the guarantee like a receipt before celebrating the answer. For a minimization problem, if OPT is 100 and alpha is 2, the algorithm must stay at or below 200. For maximization, the inequality points the other way. A 2 approximation should not promise at most twice optimum, it should promise value at least half of optimum, or an equivalent lower guarantee. Approximation is strongest when the user can live with bounded imperfection, routing trucks, covering sensors, scheduling work, facility placement, or set cover decisions made quickly enough to matter. The practical question is not only how close the answer is. It is also how fast it runs, how simple it is to implement, and whether the bound matches the risk of the problem. A useful approximation receipt names three things in one line: the benchmark, the inequality direction, and the factor that limits how bad the answer can be. Approximation algorithms are compasses. They may not reach the perfect point, but they tell you a guaranteed direction and a bounded distance from best. The promise is not perfection, the promise is knowing how far from perfection you can drift. Approximation means near optimal with proof. Ratios quantify the promise. Minimization and maximization use opposite inequality directions, so the bound must match the problem. It is different from guessing, even when the answer is not perfect. Next, we will finish with the Algorithm Designer's Toolkit, how to choose a strategy from